Right now. Am I recording? Yes. Thank God. Like I don't know if you guys saw last Thursday, I did not press the record button, and so I had to do the lecture all over again, which isn't that big of a deal. But I think I kind of nailed the lecture last week. I don't know if anyone was there. Right, right. Do it again, and then like I don't know how much I don't know how much weird experiences you guys have, but for me, I feel like a lot of times if I nail something first go, whenever I go back to do it again, I always try to recreate what I did, but that ruins the magic because the first time you do it, you're into it, you think about the math or whatever and all that. But then the second time I did it, I was trying to think like, oh, I explained this really well off the cuff. Like, what did I say? And I just confused myself. It was all over, and it wasn't as good. Um, I guess this just makes me human. So, and humans are pretty great because humans are the people that do math, right?
Yay, math.
Yay, math. Well, see, the weird thing about math, I like how we always talk about math in this class. I guess for you guys, I exist in this one little box below these two green boxes, and I only talk about math. That's the extent of my being. You're not that far off. But the weird thing about math is that it feels a little inhuman in the sense that humans are inherently imperfect, and math is all about trying to be perfect, right? It's all about like, this is a square. Like, it's a perfect square. It's not a little squiggly, it's a perfect square. This is one. It is, or this is like five. It's not 5.0000003, whatever. This is exactly five. Like, math is about like being this perfect thing. Like, the whole thing is we're trying to prove things in math beyond any doubt. Like, this is absolutely true, which feels a little bit inhuman because it's like humans exist in the real world. There's no infinities in the real world. There's no exactness in the real world. Everything has air bounds and stuff like that. And humans aren't perfect. Like, we can never really know like anything for sure in the real world. So math feels really inhuman in that sense. But I mean, what is more human than like the strive to be perfect? You know what I mean? The strive, the like to make everything as precise and perfect as possible. I mean, look at us. We surround ourselves in rooms that are like kind of perfect rectangles. We try to get them as perpendicular as possible, perfectly vertical walls. We want everything to be perfectly ordered, even though we'll never be able to actually create it in our real world, and that's where math exists to do that. Um,
Maybe the meaning of knowing goes beyond the bounds of just being human.
ooh, ooh, that's interesting. That's interesting. Oh, this now this is getting to like an awesome late night conversation about like is is the inherent state of being human trying to be more than human? Ooh, like most people that are human, like we want to think that we are like separate from the rest of our biological friends, that we're these hyper intelligent beings. But we're not that different from monkeys. At the end of the day, they use tools and stuff. That's kind of cool. Like, they have sticks and all that. I mean, we're way more advanced than them. We're way different. But in the point of like, we're not like inherently that different. And but like math is kind of that space of like, we just want to even get out of the real world. We're in like this abstraction of our real world. It's, if anyone reads Plato, he has this whole Platonic thing. By the way, now that we're off topic, we can get even further off topic. You guys know who Plato is, right? Philosopher.
Yeah.
Might have single-handedly set math back by like hundreds of years. I hate him because of that. I don't know what he did for philosophy, but I know what he did for math, and that has kind of ruined it. And the reason is because, so you guys heard of Pythagoras, that whole Pythagorean theorem? Fun fact, that wasn't him. They just named it after him. But anyway, he was the guy who had a math cult back in the day. They did a lot of cool math stuff. And one thing they did that was big was they dealt with numbers. They believed there was a purity in numbers. So they did a whole thing with like musical instruments, with like the fifths and the thirds and all that kind of thing, the halves. The whole idea was they found harmony in these whole numbers. Like, for some reason, if you took whole numbered fractions of like strings and you plucked it or whatever, it would make nice sounds and like nice, and you get intervals and all that kind of thing. And yeah, so they kind of like really, they kind of got too into it. They kind of actually worshipped numbers in a weird way. But the point is they were all about numbers. And another branch of Greek math was geometry. It was the whole thing you guys might do in high school. You have a compass and you have a compass and a straight edge. You do a bunch of geometry things. And on the surface, those are two kind of different things, like numbers and shapes. Like a square, what is that in numbers? Or 5, what is that in squares? You know what I mean? Like it doesn't, or circles, you know what I mean? Like it doesn't really make sense in that sense. So they thought of them as kind of two different things. And what Plato did is Plato had a lot of pull at the time, famous dude. He had some quote where he said something like, the only real truth in the universe can be done with a straight edge and a compass. Basically as a diss to the Pythagorean number people, going like numbers are a bunch of BS. Okay, geometry is where it's at. And so what that meant is everyone who respected Plato was like, numbers, they're crappy. Let me go to geometry. And so the Greeks just did geometry, which is cool. It's fine, but think about algebra. Think about trigonometry. Think about calculus. Think about all this kind of stuff was either inaccessible to them or hard to access because they refused to use numbers. They had to use geometry because Plato said so.
Maybe all those hurdles were because of the hubris that came out of being human.
Possibly. But anyway, hello everybody. We're a pretty full house today. Nice to see everyone. How's it going? You guys ready for fall break?
For sure, yeah.
Ready to get this over with? Is this the last class for anybody? Or does everyone have Friday classes? All Friday classes. That sucks. Sucks to be you guys. This is my last class of the week, for example. But anyway, then let's get through it. Let's get through it and get you guys to Friday. We'll almost be done. So let me share my screen here and get started. Welcome back. We are still talking about section 6.1, which is, wait a minute, I'm going to do this, and then I'll even do this. There we go. We're talking about section 6.1. And I'm going to write /6.2, which is sets. And I say /6.2 because I just kind of found out today, I was rereading the book and I was seeing, because, I like to stick relatively to the order of the book and kind of what we do, but I don't do it exactly. And I find out that I hate the way the book does chapter 6, because what they do is everything we've been doing with sets and subsets, where we talk about how do you prove something's a subset of another set, and how do you prove two sets are equal, and things like that along those lines. They don't do that all in one. They introduce subsets, and then they do a bunch of stuff, and then a couple chapters later, they actually prove it. Or actually the next chapter, they actually show how you prove a set to subset something else. Why not just do it while you're talking about it? Right? I'm no one, I guess, to complain about someone jumping around topics. I guess that's men in glass houses can't throw stones. But anyway, the point is we are here now. So we're basically doing 6.1 and 6.2 at the same time, simultaneously, because I say so. So today, though, let's get going and talking about what we left off with last time, and that is set equality. There we go, set equality. So we say, this is what we talked about last time, A equals B. So two sets are equal if and only if they contain exactly the same elements. So that's what that means for two sets to be equal. And by the way, you guys should know that equal signs are not to be used everywhere. They mean specific things and they're always defined. So for example, the equal sign with numbers is defined. Saying two numbers are equal means that the same number means something. Saying two sets are equal means they contain the exact same elements, but not everything has equal signs between them. We also use equal signs with matrices because we've defined it with that. If you go back in the literature of math enough, there's a definition of what it means for two matrices to be equal. But we don't use it for everything. For example, for sets, well, that's a different thing. The point is just be a little wary of that. But we do say sets are equal, use the equal sign. They're equal if and only if they contain exactly the same elements, which I think makes sense. That's kind of fits our conception of what it would mean for two sets to be exactly the same. And the way you could write this formally, I'll say, i.e., what this means is that A equals B if and only if A is contained in B and B is contained in A. So this is the formal, more mathematical way to look at this. And on the surface, they might seem kind of different. Like this is saying that they contain exactly the same elements. This is saying they contain each other. Why are they the same? Well, let's start here, right? How would you ever, what's it mean for two sets to contain exactly the same elements? Like, what does this mean? Well, what that means is they contain exactly the same elements. So for one, for all x in A, since they contain the exact same elements, x must be in B, right? We must have that be true. But also we want to make sure that every x in A is in B. We also want to make sure we don't miss anything. We want to make sure there's not anything in B that's not in A. So a way you could write that is there does not exist an element in B such that x is not in A. So this says everything in A is in B and nothing in B is not in A. So we want to and here, I guess. But heck, what is for all x in A, x in B? Like, how can we write this? If every x in A is also in B, what do we know about A and B? I know you guys know this. You guys got this. If every x that's in A is contained in B,
For all x in B, then x is in A.
well, not necessarily, right, Safa? But thank you for thinking, though. Like, for example, if we had like 1, 2, 3, and 1, 2, 3, 4, right? Everything in this set's in this set, but not everything in this set's in this set, right? 4 is in this set, but not here. But if you can prove that everything in A is in B, so every element in the set A is contained in B, that means the entire set A is contained in B. This is the exact definition for A is a subset of B. Right? This is what we learned like 2 classes ago. This is the definition for A is a subset of B. And then let's deal with this, right? If we don't have, so if we know that there doesn't exist an element of B that's not in A, well, what this is really saying is that for all x in B, x is in A. If you distribute that negative correctly and you negation correctly and you flip the quantifier and do what you're supposed to do, you get that. But what is this?
Is that B is contained in A?
Exactly. This is saying that everything in B is contained in A. So all of B is contained in A. This is B is contained in A. So the point is that's why these two ideas are the same. If A and B contain exactly the same elements, that means everything in A has got to be in B and everything in B has got to be in A. That's what it means to be the same. And one really easy way we can look at this is through the lens of Venn diagrams. And so this is the Venn diagram way to look at it. And I'll say Venn diagram. If A equals B, right, that means like if this is the set A, well, the set B is just exactly this, right? A and B are just the same thing. And clearly from here, you can see, oh, well, if they're equal, then A is inside B because A just is B, and B is inside A because B just is A, right? And this works the other way around, right? If A is contained in B and B is contained in A, well, the only option is for them to be the same circle. Because if they weren't the same circle, then there would be something in A or something in B that wasn't in the other one, which can't happen because we're assuming A is in B and B is in A. But if they're the same circle, A equals B. So this is like 4 different ways to look at it. Anyway, this is what it means for two sets to be equal. Any questions? My finger looks really big, doesn't it? Like, look how big my left hand is compared to my right hand. I'm deformed. Sorry. Anyway, so there you go. No questions? Then we can move on and do an example with this. And here is our example. The set 6z, well, I'll just say what it is. So 6z, this is the set of all things in the form 6k, such that k is in z. I haven't formally defined what it means to have like a number in front of z here, but I hope you guys are getting it. It's just, you can think of it as 6 times everything in z. And then we'll call this A. And then we'll call B, that's going to be the set of all x in the natural numbers such that there exists a k such that x equals 3k and there exists a t such that x equals 2t. So this is going to be B. And actually, I'm sorry, I want to write this differently. But I'm going to rewrite this, don't worry. B, what I'm going to write it as is going to be 3z intersect 2z. We haven't defined this yet, but by the end of the day, we will. And what that's going to end up meaning is going to be an x, and then in the integers, x in the integers, such that there exists a k, such that x equals 3k, and there exists a t, such that x equals 2t. And just to give you guys a little preview, right? If there exists a k such that x equals 3k, this means x is in 3z. There's just a t such that x equals 2t. This means x is in 2z. So if B is the set of all x that are both in 3z and 2z, that gives you an idea of what the intersection is, right? Intersection, we've heard that before. It's everything in both. We'll see that in a second. But anyway, this is what B is going to be. And here's my claim. (6e), or I'll say A, is equal to B. And here's how we prove it. So the way you prove A equals B is we use the formal definition. And that is A equals B if and only if A is contained in B and B is contained in A. A is a subset of B and B is a subset of A. So the way you prove A equals B is you first prove this guy and then you prove this guy, or whatever direction you want to go. And so what you do with that is, and really a lot of people write it, instead of saying B is contained in A, they write it the other way around. They say A is a superset of B. A contains B. Same thing I just wrote down, except I just kept the order of A and B the same and just changed that from is contained in to what contains, I guess you could write it. Hope that makes sense. So the proof, though, goes like this. We're first going to prove that A is a subset of B. We're just going to prove that. So I'll say here in pink, just so you guys know what's going on, we want to show that A is a subset of B. And by the way, this symbol I put in parentheses here, this is not just for me. This is a standard math technique. You guys should write this in your homeworks and tests and things like that when you're proving this side of the containment. So we want to show that A is in B in this first side. And so the way we do that is, well, how do we prove that A is a subset of B? Well, A being a subset of B means that every X in A is in B. That's what it means by definition, right? You can write that in green somewhere in case we forgot. A and B is equivalent to, for all X in A, X is in B. Universal statement, right? So the whole thing we did last class, which is called, this is called the element method, is by just showing that every element of A is an element of B. That's why it's called the element method. And so what we're going to do here is let X be any arbitrary but particular element of A. Now, to finish the proof, we want to show that it's in B. Well, what do we know about elements of A? So A is 6Z. So the one thing we know about elements of A in general is that they can be, that they're multiple of 6, right? So thus, by definition of A, X equals 6K for some K in Z. All right. So we have this X, which is in A, and we know it could be written as 6K for some integer K. We want to show A is in B. So we want to show that this is also in B. This X is in A, we want to show it's also in B. So how can we show that this X equals 6K is in B? With the bystander effect, so many of you today. So in order to be in B, every element of B, right, this is just basically saying X is divisible by 3. And this is basically saying X is divisible by 2. So if X equals 6K, we need to show that means X is divisible by 3. It can be written as 3 times something. And we need to show it's divisible by 2. It can be written as 2 times something. So what's our strategy here? This is a homework. What would you try to do? I'm not frozen, by the way. I'm still here. Someone throw an idea at the wall. What do we got here, people? So we have X equals 6K. I want to show it equals 3 times something.
Well, we know that X equals 6K is the same thing as X is equal to 2 times 3K, right?
Thank you, Herman. That does both at once. Yes. Note, X equals 6K and 6 equals 2 times 3. This is going to be 2 times 3 times K, which I'll do 2 first because I wrote in this order. This is 2 times 3K. And then I'll say, since 3 and K are integers, and Z closed under multiplication. Because we have that, 3K is in Z. Let T equal to 3K. Then T is an integer such that X equals 2T. So we're proving for 2 first. Easy. Yeah, it's all good, right? Because x equals 6 times something, it definitely equals 2 times something. We do the same thing with 3. I'll say further, like that word further. Further, x equals 6k, which equals 3 times 2k. I'll call it k prime equal 2k. Note, z closed under multiplication and 2 and k and z. Thus, k prime, which equals 2k, is in z. Hence, x equals 3k prime for some integer k prime. It's an exclamation mark. It's a prime period. There we go. So we know that x can be written as 3k and x can be written as 2t for some integers k and t. Therefore, x is in B, right? Because B is just all integers that can be written like this. So I'll say hence, or I'll say therefore, since x equals 2t and 3k prime, x is in B by definition of B. And the very last line here, thus, A is in B. So all of this work was just to prove that A is contained in B. To prove that A actually equals B, we have to show it goes the other way around too. Well, any question on this first part? Good. I think we're quiet but understanding. It's good, I guess. Yeah, that's cool. So now we need to prove this part, the opposite of the containment. We literally write this right here. And for sake of room on the board, I'm going to erase this first part, but you guys would keep going in one line here, or keep going the same proof. Will this upset anybody if I erase? We're good? Okay, no one's screaming. So, just testing the waters. So let's go ahead and do this right here. So here we want to show that A contains B. We want to go the same way. So trying to show that A contains B, what this is saying is that every element of B is in A. So once again, using the element wise, we're going to say let X be any arbitrary / particular element of B. Just like that. Then by definition of B, there exists a K and Z such that X equals 3K, and there exists a T and Z such that X equals 2T. And this is literally by definition, right? X is a set of all things that satisfy this. So if X is in B, well, then it looks like this. All right. Now we have the slightly harder task of showing that if X equals 3K and X equals 2T, X has got to equal 6 times something. And here's where I will take over, because this actually uses a pretty interesting thing that we proved before, but I won't expect you guys to necessarily pull this out of your notebook. So so let's say if this is the case, if we know this is true, let's notice this. Thus, 3k equals 2t, which implies that 2 divides 3 times k. Actually, we can play with this. 3 times k, that equals what? 2 times k plus k, right? Since 2 divides 2k plus k, which is that, and 2 clearly divides 2k, then 2 divides k by theorem from homework, I believe. Right? We put that one theorem that said if it divides the whole thing and divides one part, it must divide the other part. Yeah. I think this makes sense too, right? When we think about it. This is saying 2k plus k is a multiple of 2, and 2k is a multiple of 2. So that means this little bit left over has got to also be a multiple of 2. Yeah. Yeah. Another way to look at it is this is saying that 2k plus k is even, and 2k is obviously even. And so this is saying even plus something's an even, that means that something's an even. And I hope this makes sense. So 2 divides k from theorem from written assignment. Therefore, x, or therefore k equals 2c for some c and z. That's just definition of divisibility, right? 2 divides k equals 2c. Then x equals 3k. So we're going to go back to the 3k, but now there's something special about k, and that is k equals 2 times c. This is 3 times 2 times c, which equals 6c. And why is that important? Well, that's exactly what we want to show that x is an element of 6z, an element of a up here. It's just any integer times 6. Ergo, sorry to use therefore, ergo, since c is in z, x, which equals 6c, is in a. By definition, hence b is contained in a, or a contains b, same thing. Any questions on this? So this side was a little bit harder. You had to be a little bit creative, right, in finding and figuring out why the heck 2 divided k. Once you know that x equals 3k and you know that x equals 2t, really the thing you need to be thinking about to get that 6 divides x is you get that either 2 divides k or 3 divides t. And both have to happen here via what we called, I believe, Euclid's lemma. Yes, it's Euclid's lemma. And Euclid's lemma in general, just a trip to memory lane, says that if p is a prime, if p prime and p divides ab, then p divides a or p divides b. I believe we actually proved that. And so clearly here, since, for example, 3k equals 2t, well, that means 3 divides 2 times t. Well, 3 is a prime that divides this product, meaning 3's got to either divide 2 or t, or both. But it doesn't divide 2, so it's got to divide t. really random thing. We got around in this case, but in general, you could use Euler's formula for something like that. Euler's, not Euler's, Euclid's. Euler did everything else. Euclid did that. But anyway, so we proved the containment in the one direction. Now I proved containment in the other direction. So then we can end off by saying, therefore, since A contains B and B contains A, we have the edge of that glare. Look at that. A equals B. Square it, done. Any questions? This idea is beautiful and weirdly powerful. And that is, you would think that showing two sets are equal would be easy, but it's really not. Because especially like these are infinite sets, right? Once you're dealing with infinite sets, sometimes they might look weird and differently from each other. When you're dealing with those things, it's not at all obvious that two sets are the same sometimes. But this idea of showing they contain each other is a really nice in, and it totally works. We good? Good. I feel like you guys don't understand how good of an end this is. But yeah. This is like if you're at a job fair and you know, whenever you go to a job fair, it's always weird to start the conversation with the person there, trying to find something or whatever. And then you find out that the person at that job fair, like, is also a really big fan of that really funny show that not a lot of people know about but you. And then you're clicking. You got that in. Now you know how to talk to them. Now you know where to go. I don't know. The point is, well, that's really what I mean by foothold is that the double containment gets you in the door. It gives you something to grab onto and something to do, which is interesting. I don't know why I thought of it as job fairs. I hate job fairs. But anyway, the point is, let's do another example. So an example is, wait, where do I want to be? Yeah. So claim, well, actually, first I'll define what A and B are just to keep it simple. So let's say A equals the set, and that is X in the real numbers such that X is not in the rational numbers. What is that set known as? If you're not rational, what are you?
Irrational.
Thanks, Safa. Nice. Thanks for the confidence. I love the 30-second pause followed by absolute confidence. You usually have to pause like that. Like usually if you're at a spelling bee and a person takes a while, they're shaky. They go like irrational, I-R-R-A. But they usually don't take 30 seconds. They just nail it. Just go irrational, I-R-R-A, like they do it the whole time. Anyway, so yeah, that's what A is. Let's say B, a slightly different set, E equals all X squared such that X is an R and X is not the irrationals. And here's the claim. A equals B. This one's weirder, right? This one is really weird, where it might not be obvious these sets are the same, but I claim they are. So let's prove it. And the really nice way to get your foot in the door is this double containment thing. This is what we're going to do as always. And so what we're first going to prove is this direction. We want to show that A is contained in B. And this will turn out to be easier, I think. So we want to show that A is contained in B. So what we're going to do is remember saying that A is contained in B means that every element of A is an element of B. So we can use the whole direct proof idea of just let A be an arbitrary element. Let's go ahead and let let X be any arbitrary / particular element of A. Then let's just write down, we're always going to do this, right? Like, let's write down what we know about A. Then X is in R and X is not in Q. So now we really want to show, to really prove this, what we need to show is that X is in B, meaning X is some square of an irrational number, right? Like if X is in R and it's not in Q, that means X here is an irrational number. So B is the set of the squares of an irrational number. So we want to show that X is the square of some irrational number. And actually, I made a key error that I'll justify right now. I meant to say this. Positive. Positive. There we go. Because if it wasn't positive, then clearly it'd be wrong because the square of any real number is positive, but not every real number is positive. So we need that positive situation to make everything work out. But anyway, yeah. So then X in R and X is not in Q. We want to show that the square root of X essentially is in square root of X is irrational, right? We basically want to show that the square root of X is in R and the square root of X is not in Q. Because if we show that, because then X would equal the square root of X squared. So then X, right, would equal some number that's a real number and not a rational number such that, such that X squared equals that. So actually, I'm going to change this to a Y. Not because this is wrong at all, just because I don't like all these X's floating around. It feels confusing to me. So now basically, we want square root of X to be our Y. That's some irrational number, right? Because then you square it and you get X, and that works out. Does that make sense? The fact that if we get the square root of X to be irrational, then X is going to be in B. Because if the square root of X is irrational, you can think of Y as being the square root of X. And then because Y is irrational, Y squared is going to be in B. So as long as square root of X is irrational, square root of X squared, which is X, will be in B. Hope that makes sense. Let's talk about how we do that. So, crap, we're out of time. I wish I could sit here and stare at the screen blankly for all of time with you guys, but sadly I have to keep moving. So I kind of go through it. This is very, very similar to a proof you guys had in your test. That one test problem proving the cube root of rational numbers are not rational. The way we do that goes like follows. So really we want to show that the square root of X is not in Q. Clearly it's in the real numbers plus, right? But it's not going to be in Q necessarily. So let's go ahead and assume for contradiction. Assume for contradiction that the square root of X is in Q. So that means it equals A over B for some integers A and B. Then X squared is going to equal A over B squared. Then X is going to equal A over B squared. But that means if X equals A over B squared and A and B are integers, what does that mean about X?
X has to be a rational number, right?
Yeah, but X is defined to not be rational. It's specifically irrational. So this is the contradiction. So if x is an irrational number, we can guarantee its square root will be an irrational number, which guarantees that x, which equals the square root of x squared, is in B. Fascinating. That's right there. Let's assume. So we're gonna have a contradiction proof inside of here. This is like, I'm trying to show you guys we can link proofs together, combine them whatever way as we want, as long as it all works out. So as long as they all fit together. So assume that, or I'll say consider, just to introduce it, square root of x. Note since it's real number positive. Note since x is greater than or equal to 0, the square root of x is an r. Plus. Because x is greater than 0, square root of x is also an r plus. Also real number greater than 0. Assume, for sake of contradiction, that the square root of x is in the rationals. Thus, there exists an a and b in the natural numbers, and the integers, and the integers, such that b does not equal 0, such that the square root of x equals a over b. Then, squaring both sides yields, fun word, yields that the square root of x squared equals a over b squared. And then this equals x, a squared over b squared by undoing square root and distributing square to a and b. But then note, since a and b are in Z, and Z is closed under multiplication, a squared and b squared are in Z, right? A times a and b times b are both in Z. They're both also integers. Thus, x, and I'll say further, since b does not equal 0, b squared does not equal 0, thus x, which equals a squared over b squared, is in Q. Contradiction, x is defined to not be rational. Thus, our assumption that the square root of x is in Q is false. Hence, if the square root of x is not in Q, x must not be in Q. Meaning x is irrational. Or sorry, square root of x. So all they have is to prove the square root of x is irrational. Then since y, which equals the square root of x, is in our plus, and y is not in Q, y squared is in B, by definition, I'll say thus again because I'm too bored to think of the connecting word. Thus, not bored. I'm too ingrained in the math to get caught up in the English. Thus, x, which equals the square root of x squared, which equals y squared, 1b and b. There we go. So we showed that if x is an irrational number, the square root of x must also be an irrational number, which shows that the square root of x squared, which is just x, is in b. Hence, I said hence twice. Ergo, I don't know. Then. Then's a good word. I already said then. I'm running out of words. Ergo, A is contained in B as desired. So this is the first direction. Any question on the first direction? Good. But let's hit that second direction, which again, normally you guys would do below, but because of limited whiteboard space, I really wish I had like one of those mega chalkboard things where you can roll them over each other and roll them across each other, and have like five chalkboards going at once. I really wish I was able to get that in my home, but sadly I'm zoned in a residential neighborhood that would require construction. But anyway, let's say maybe I can build it myself. So now I want to do this right here. So now I'm trying to show this side, and here we want to show that B will be contained in A. We already know A is contained in B. We want to show B is contained in A because if they contain each other, they must equal each other. It's the same idea here, right? The idea is just, let's just consider any arbitrary element in B and try to show it's in A. So let's B be any arbitrary / particular element of big B. Then, by definition, B equals y squared for some y in R plus and y not in Q. So for some irrational y. So we know y is irrational. So we have b's in big B. We want to show little b's in big A. And all you need to do to be in big A is be irrational. So basically what we're trying to do here is show that if y is irrational, then y squared, which equals b, will also be irrational. Because that places b in A. Little b in A. But also that eventually places big B in A. So either way. The point is, I'll just show that y squared is also irrational. Oh my gosh. I'm obviously wrong. This was meant for a one subset example. Why am I obviously wrong? Can anyone think of an irrational number whose square is not irrational? I'll give you a hint. We called it one of the most famous proofs in mathematics. We were talking about it. The square root of 2. We proved that's irrational, but if you square it, you get 2, a very rational number. So I don't know what I'm doing here. Sorry about that, people. I meant this was supposed to be an example of this. There we go. So that's good. So we proved that A is a subset of B, but B is not a subset of A. Why is B not a subset of A? So actually, we can salvage this. We can prove this. We can prove that A is a proper subset of B. So the proof would go, we'll do this like we already did. right? So we come down here and we eventually get thus A is a subset of B. Now, in order to not be a proper subset, all I have to do is show that there's some element of B that's not an A. Wait. Yeah. And real easy. I'll say note, or I'll say consider B equal the square root of 2. Or no. Consider, yeah, B equal 2. Note, B equals the square root of 2 squared. And since the square root of 2 is in R plus, and the square root of 2 is not in Q, B, which equals the square root of 2 squared, is in big B by definition. However, B, which equals 2, is in A, or sorry, is in Q. So B is not in A. Therefore, there exists an element of B not in A, mainly 2. So A is a proper subset of B. That's what this is supposed to be. Does this make sense? Sorry for that blunder. We're not proving that they're equal to each other. We're proving that A is a proper subset of B. To prove A is not a proper subset of B, we had our nice proof that A is contained in B. But to prove it's a proper subset, we need to show that A is not all of B. Otherwise, A just kind of equals B. And so why would we call it a subset? It would just be equal. So that's why we call it proper subset. So a proper subset of, so in order to show that A is a proper subset of B, we have to show there exists at least one element of B that's not in A. To show that A is not all in B. And that element gives us 2, because 2 is totally in B, but it's not in A. Any questions? All right, cool beans. So that had a few complicated proof techniques together. That's one of the classic examples that we do in class. It'll be harder than the homework. And before we leave, let's just talk about set operations real quick. Sound good? We're still in this section. Now we're talking about set operations. So we're going to have a few different operations. I'm going to color them. Let's say we're going to have the union, the intersection, and the complement. So I feel like you guys might have heard some of these before. So we're going to do union first. So A union B we write as A, we get like a big U sign B. So A union B or as A big U sign B. And what it is it really equals the set of all x such that x is in A or x is in B. i.e., the combined set of everything from A and everything from B. So, for example, if our set was stuffing, dressing, and turkey, union, mashed potatoes, what's some good Thanksgiving stuff? Come on, we're being festive. Mac and cheese. Anything else? Favorite Thanksgiving meals? Dishes?
I like pumpkin pie.
Ooh, pumpkin pie salad, Safa. What do I say about pumpkin pie is that it tastes nothing like pumpkins. But I like it. So all of this stuff, right? The union of this is just the combined set. It's the set of stuffing, dressing, I already wish I wrote less, turkey, mashed potatoes, mac and cheese, and Safa pumpkin pie. So that's what a union is. It's just you put everything together. And it's really tempting to think of a union as an and thing, as being like this and this set, but it's actually better to think about it as an or thing, as in X is in the union if it's in A or it's in B. So if you look at this union, right, mac and cheese is in the union because it's in this set or this set, happens to be this set. Pumpkin pie is in the union because it's in this set or this set. Yeah, and I'll draw a Venn diagram real quick. The union, the Venn diagram, if you had an A like this and a B like this, the union is just everything. But it's time to go. So that's our basic introduction to unions. We'll do more next time. Any questions on this?
Will we be able to do all of the quizzes?
I believe so, because I think I was conservative with what I put out, but I will go make sure right now. Actually, wait, stay here real quick. If you want. You can leave if you want. Thank you, everybody. If you want to leave, have a great Thanksgiving break. Yeah, hopefully get your homework done today, and then you'll have no discrete math to do. Just be hanging out. All discrete math you'll be doing because you love the game, not because you need to. But yeah, let me check these quizzes. If you want to stay, I'll tell you right now while you're on the line. Discrete math. Let's go to, let's see, quiz 1. Definitely do quiz 1. Quiz 2. Okay. So I'm taking quiz 2 off. Look at that. Okay. So, just quiz 1. Quiz 2 and 3 are going off because, so it turns out you might think, well, hold up. How did we spend a whole week on chapter 6.1? We can only do 1 quiz. And the answer is because actually a lot of what we learned was chapter 6.2 in secret. So really chapter 6.2 is going to go by in like 30 seconds. It's going to be like, remember what we did here? That's chapter 6.2. Like all this set of quality stuff we did right now, that's chapter 6.2, technically. But I don't understand why you'd mention set of quality and then not actually prove anything with it. Anyway, the point is, that's why my quiz is a little out of order. But yeah, so chapter 6.1, we're in assignment 11, only 2 questions. You guys lucked out this week. And then just have a good break.
Thank you, Professor. Thanks for the
What?
Thanksgiving miracle.
You're welcome. You're welcome. Yeah. No, have a great break, Stop. You do anything special?
I'm just going back to Nova, but I at least get to see my family. I haven't seen them in a long time.
Yeah. I'm with that, Safa. We'll have a good break. Have
Thank
fun,
you.
family.
Take
Yeah.
care. You too.
You're welcome. You're not gonna invite me to your Thanksgiving?
I mean, you can come down to Lorton if you want, or Nova. I live in Lorton. Let me know. My door's always open for you.
Thanks, Safa. That's the right answer. Or probably
Just
the wrong
email me.
team and a professional relationship here, but I appreciate the gesture.
Peace,
Have a good day.
Professor.